Hello, everybody. Welcome to the NSERC PermafrostNet webinar series. Thank you for joining us today. It's our usual time of 1 p.m. Eastern on a Wednesday. Today's speaker is Andrew Clark. He's going to be presenting on advancing Arctic coastal erosion measurement and monitoring through UAV-SfM and object-based image analysis. I'm going to provide a short little introduction of Andrew, then I'll hand it over to him for his presentation. After the presentation, we'll have a Q&A. Feel free to either wait until the end or to post your questions in the chat, and I'll present them to Andrew at the end, or you can turn on your camera and ask him yourself. So if I can introduce Andrew. Andrew completed an MSc in environmental science at the University of Prince Edward Island, where he studied the geomorphology of the sandy coast of PEI. Andrew's interest in coast stems from his upbringing on Prince Edward Island, where you're rarely further than 20 minutes from the coast in any direction. He recently completed his PhD at the University of Calgary in the Department of Geography under the supervision of Dr. Brian Moorman. His PhD research is focused on remote sensing of Arctic coasts in the Western Canadian Arctic. He'll tell you all about his research in his presentation, which I'm really looking forward to. And he's done so well that he now works as a senior climate data and policy analyst at the climate adaptation section of the PEI government. Part of what he does is coastal hazard mapping and development of shoreline management plans. Personally, Andrew has a passion for throwing frisbees, whether it's for his dog in ultimate or playing disc golf. So I'll now hand over to Andrew.
Right on, right on. Thanks, Tristan. Thanks for joining. Good afternoon, I guess good morning for some. Yes, so as mentioned, I finished my PhD recently, traveling back to Calgary from PEI in January to defend. So today for this talk, I'm kind of just going to go back to that work, give a bit of an overview of the different components of that, and share some of the highlights, I guess. So that being, what I focused on was trying to advance Arctic coastal erosion measurement and monitoring through UAV-SfM and object-based image analysis. Before we get started, a little bit of background, where Arctic coasts already exhibit some of the highest rates of erosion in the world. This is despite a limited open water season, usually June to October. This is because of the presence of permafrost, meaning that the coast is subject to thermal and mechanical erosion, as opposed to temperate coasts, which are subject just to mechanical erosion. The presence of permafrost and massive ice and the above average warming in the Arctic mean that coastal erosion in the Arctic is expected to increase. Naturally, climate change will lead to a longer open water season, increases in storm severity and frequency, and a reduction in summer sea ice extent, which means there's an increase in fetch. So the wind is able to transfer its energy more efficiently into creating a more energetic wave climate. Also to that is there's a consequence of Arctic coastal erosion is the release of previously frozen sediments that contain organic carbon that when released through erosion degrade into carbon dioxide and methane. These gases make their way into the near shore and eventually to the atmosphere. And this represents a potentially large source of greenhouse gases, considering that Arctic coasts represent 30 to 34% of the world's coast. And these are not accounted for in the current global climate models. So all of this is to say that Arctic coastal erosion has implications at the local, regional, and global scale, but they're not fully understood or well quantified. As a result, the primary objective of my PhD research was to advance the measurement of Arctic coastal erosion, and I did this by focusing on two emerging technologies, UAV-SfM and object-based image analysis. also known as OBIA or GEOBIA. That's probably what you'll hear me say throughout this talk. UAV-SfM, that stands for Unmanned Aerial Vehicle Structure for Motion. When we use drones for mapping, this is what we're doing. We're taking images of an object from multiple angles, so overlapping images. And in our case, it's the coastal environment, and we're reconstructing that scene as a 3D object or digital surface model. And we also get a seamless ortho image from which we can make measurements. UAV SFM, it is an important new tool available to researchers because of its ability to create high spatial and temporal 3D data sets. And OBIA, GEOBIA, stands for Object-Based Image Analysis, which signifies a new approach to image classification that is particularly useful when using high and very high resolution imagery where there can be a lot of noise present when using traditional form of pixel-based classification. The idea of GEOBIA is to segment an image into homogeneous regions from which we assign meaning to based on its characteristics to create an image object, which then we assign meaning to as a class. An image can be segmented in any way you want to fit your application, but at the end of the day, you're vectorizing a raster image that you can then use for measurement and analysis. And in my case, I'm looking to assign meaning to the boundaries between classes. I'm using these technologies to investigate along three primary themes that specifically contribute to better understanding the coastal processes in the Arctic. The themes being planimetric and volumetric quantification, multi-proxy analysis, and semi-automated feature extraction. And I'll elaborate more on what I mean by these. Some more context on Arctic coasts. We have two coastal types that are unique to the Arctic. On the left is a retrogressive thaw slump, which develops because massive ice melt and brings upland sediments to the coast. Block failures on the right form when wave action undercuts the cliff, and the ice wedge polygon interface loses cohesion and causes these large sections of coast to break off very, very quickly. And if you look closely at the bottom right image, you get a sense of scale where there's a helicopter and a person that are made to look pretty small. So these types of coasts are just some examples of major sediment release that can occur from Arctic coasts. Even more context, I want to take a bit of a step back and elaborate more on what I mean when I refer to multi-proxy analysis. And this brings up sort of this seemingly silly question of what is a coastline? Surprisingly, in the coastal literature, there's not a great deal of emphasis put on the choice of coastal proxy used in the analysis. Usually there's like a short sentence stating what the proxy was that was used, but not really a discussion of what consequences this has on the analysis of what the analysis is telling you. So there's a number of coastal proxies that can be used, like different water lines, different vegetation lines, different land features. Ultimately, the choice is going to be application dependent, but also data dependent. So where particularly in the past when the coastal proxy used was dictated by the imagery and what was best resolvable. So if you just kind of scroll through image resolutions, it's pretty clear that as you decrease image resolution, you're sacrificing identifiable features. And then further to this, in the Arctic, where you have complex environments like retrogressive thaw slumps, the water line, for example, doesn't adequately capture the morphological change, particularly over short time scales where there's multiple sources of sediment release and by consequence, greenhouse gas release. So I'm sort of contending that tracking the change of multiple coastal proxies is necessary to tell the whole story, and particularly because we have all of this high resolution imagery available to us now. What was once a limitation is now a strength, but it hasn't really been broadly implemented yet. So I structured my thesis into 4 manuscripts, where the first 2 focus on using UAV-SfM data, while the last 2 focus on using satellite imagery. Paper 1 and 2, I develop along the themes of multi-proxy analysis and volumetric analysis, and then as well as object-based feature extraction. Paper 3 and 4 is more focused on multi-proxy analysis and object-based feature extraction. So there isn't really a temporal aspect to those. In my first paper, it is very much a technical validation of UAV data collection methods. Um, it's fairly straightforward to collect and process UAV data, and you get these amazing data products that they seem accurate, but as we'll see, that's not always the case. So for this, I present a number of different scenarios that vary the flight pattern, imaging angle, and georeferencing strategy. What I found was that including oblique images to the image block can improve vertical accuracy and mitigate systematic error that results from radial lens distortion. And then looking at a high level, this figure is showing the resulting digital surface models generated for the different scenarios. And it's pretty clear that there's quite a bit of variability depending on how you collect your data. But overall, the message being from this was that not all UAV SFM data are created equally, and particularly when conducting volumetric analysis, where the Z accuracy is important. There should be a little bit more care taken in how you collect your data and then how you subsequently report on your data. Paper 2 is where I first introduce object-based image analysis and further develop and refine the idea of multi-proxy and volumetric analysis that I first introduced in paper 1. So for this, I looked at 2 coastal sites that had varying degrees of complexity, a retrogressive thaw slump known as Peninsula Point, and Tuck Island, which protects the harbor from open ocean and has a long history of high erosion. I created object-based classifications from which I then used the boundary lines between the classes to extract these proxies. For this, I relied heavily on using thresholds, such as the mean spectral values, elevation, and slope to get the classes that describe the land cover. So at Tuck Island, there was the beach, water, cliff, and tundra classes. At Peninsula Point, I needed to introduce a few more classes to account for the active and inactive areas of the thaw slump. But in the end, we get these classified images, which we can then extract coastal proxies in a GIS based on the boundary lines that exist between the classes. Here I extracted the water line, the cliff toe, and the cliff edge, and then compared those against the same features which I manually digitized for the coastal change analysis. As some of the first research in this area, I was pretty happy with the results, where in many cases the extracted features were within half a meter or so of the reference features. But there is an obvious problem with the water line, for example, and this was for 2 reasons. UAV SFM doesn't recreate water surfaces well, and so this underlying data wasn't suitable for the analysis. And the interpretation of the water line is also difficult, where it's not always well defined because it's a moving feature. Similarly, the cliff toe and cliff edge are not always well defined, and there's a bit of subjectivity in the interpretation and and also how the computer interprets these features, particularly in the retrogressive Gauss lump environment where there's multiple edges present. So for the multi-proxy and volumetric analysis aspect of this paper, I started with the cliff toe and cliff edge at time 1. In theory, you would use GeoBia to identify these features, and then at time 2, I identify those same features. The most common method for measuring planimetric change is to use transects that intersect those features at different times. But what's novel here is that for a given transect, I have cliff toe and cliff edge movements. And as well as by subtracting the DSMs, we can create volume change segments where adjacent transects bound an area that can be then associated with a transect. So the idea of this is to create a more comprehensive analysis where instead of just having a single measure of a single proxy along the coast, you have planimetric movements of multiple changing features, as well as the volume change associated with that location. And here we're just looking at the multi-proxy planimetric and volumetric change in schematic form, and then a quantification of the change that occurred across these 3 dates of data collection. And not to dig too far into this or look too closely at the exact numbers, this approach was used to look at high temporal changes at these sites, showing the impact of a storm event and seasonal time changes. And we found that the reported change of each coastal proxy and subsequent volume release was temporally dependent. So, for example, the change in the cliff toe occurred during the storm event, while the erosion of the cliff edge kind of caught up over the seasonal time scale. And then for the water line, this could move seaward and it could move landward depending on the sediment supply in the nearshore. But ultimately, I see UAV-SfM as being a really useful tool for understanding and monitoring short-term changes to the coast. To move forward for paper 3, I really developed along the themes of multi-proxy analysis. So I'm identifying multiple coastal indicator features from remote sensing imagery and object-based feature extraction. But this time I'm scaling it up to look at a broader area using high-resolution satellite imagery. For this, I conducted analysis of a single coastal scene in the Western Canadian Arctic. And as the first time utilizing an object-based approach on satellite imagery, I did some testing on classification approach. So there was threshold, supervised, and deep learning CNN. Tested different image resolutions to understand applicability across imaging platforms. And then I iterated object creation to identify what the ideal parameters are in this environment with this data source. In this, I created a simple classification scheme that uses tundra, water, and then everything else in between I classified as coastal boundary zone. This simplification meant that I could ignore some of the complexity that's present in the coastal zone, where in this case the imagery was really only reliable enough to identify the tundra or the cliff edge and the water lines. Another benefit to using satellite imagery as opposed to UAV-SfM was that we had access to the near infrared band, which meant we could use vegetation and water indices to basically classify the majority of the scene. In the end, I created vectorized classifications, tested different classification approaches and different segmentation scales. From this, I used a GIS to extract boundary features to create multiple coastal proxies. And here I'm showing just a sample of different locations where the blue line represents the reference features and the extracted features are in red. So at times there's near perfect agreement. Other times the algorithm is sort of interpreting the features differently. And then sometimes the complexity of the area leads to poor image objects. Um, the classification accuracy depended mostly on the image resolution and the classification approach, where we were able to achieve quite high accuracies using the deep learning CNN classifier, um, which tended to be more accurate with small segmentation scales, suggesting that at a certain point you start to undersegment your image and is sort of generalizing your image too much. To assess the accuracy of the features, like the waterline and the tundra line, I created increasing buffers around the reference features, which were manually identified. Then for a given buffer size, I report how much of the extracted feature falls within it. Here, the color of the line represents the image resolution, and the symbol on that line represents the classification approach. Um, Overall, I was able to get about 50% of the extracted features to be within a few pixels, so 1 meter or so, using 50 centimeter satellite imagery. So this was, yeah, within a few pixels of the reference feature, and this is the general allowable tolerance for manual interpretation. This this is significant because it represents a potentially 50% or so reduction in workload, but also lends itself to small manual reclassifications being made so that you could further increase your extracted features in a pretty easy way. Um, and then yeah, it was really a nice starting point where some of the remaining 50% can be explained by anomalies, but obviously there's more work to do on this. So, which leads into paper 4, kind of the culmination of the thesis, which I took a lot of the aspects learned in paper 3 and 2, um, and continued that as a chance to further refine the object-based algorithms and expand the scope of the analysis to include other representative coastal types and assess the feasibility of applying this approach at an even broader scale. So for this, I looked at 3 coastal stretches in the Western Canadian Arctic, the entire coast of the Yukon, the coast of the Tuck Peninsula, and the western coast of Darnley Bay. And this amounted to over 500 kilometers or so of coastline. With this, I took a more generic approach, so that it could be applicable across the coastal environments and capture more variability in the satellite scenes. So I came up with a classification scheme that started with a um, more detailed classes, which would then help in distinguishing classes that had similar spectral characteristics. So the wet sand often looked like nearshore waters. So those would be their own classes, and then eventually get merged into beach or water, respectively. Um, for this, again, able to achieve pretty high accuracies for the classified images, particularly when considering the generalized classification, although there was some variation between image scenes, just due to different conditions and different complexity of the environment. The feature extraction accuracy was largely influenced by the coastal environment and varied between the features. Because we were looking at such a large area, there tended to be a lot of situations where there were outliers. So if we kind of just look at the median statistic, where we throw out the outliers, basically, there's often good agreement between the reference features and the extracted features. And then similar to paper 3, we have blue lines, which are the reference features, and the red lines as the extracted features. And we see the same general trends where there is well-defined features, the object-based extraction does very well, but it's in areas where the this idea of the coastline is a little bit more subjective, and the agreement between the lines isn't always great. So in the end, the take-home message is that while the object-based approach doesn't get it right everywhere, it does particularly well along erosional coastal types, where the features tend to be more well defined as opposed to depositional coast, where determining the coastline is a challenging task even for a human interpreter. And then if you consider this in the context of measuring Arctic coastal erosion for the purpose of quantifying greenhouse gas emissions through sediment release, there's actually a pretty strong case to make. And then in addition to that, the resulting vectorized classifications can be a valuable data product that have additional potential applications. So thinking about future work, it would be great to have kind of develop a system where someone could upload their image and then they're provided with a generalized classified image, um, which then they can apply to for their own purposes. And then also the incorporation of Arctic DEM is seen sort of as the next logical step towards volumetric change quantification at a broad scale. So that's the overview of my work. I'm happy to take any questions.
I have a question. Thank you very much for your presentation, first of all. I was wondering if you could talk a little bit about your data products, or what the data was collected. I assume it was some kind of directly georeferenced product from manned aircraft. And yeah, how did you deal with uncertainty, vertical uncertainty in your DSMs when you calculated volumetric erosion along such long strips of coast?
Yeah, calculating uncertainty of volume measurements is actually something I learned that's kind of hard because it's such a big area. It sort of compounds. But first two papers using UAV-SfM, we had set up a base station on an unknown point, ran it for 5 hours or so, distributed ground control points, RTK'd them, used that for georeferencing. So those products are pretty good, particularly when you use oblique images in the image block, which I tried to implement in all the products post kind of that first analysis. So we get, if you're familiar with UAV data that is georeferenced with RTK, it is kind of silly good, within 5 centimeters or so. So um, pretty fortunate to be working with data sets like that. The two latter data sets were latest satellite imagery, and then pan sharpened to 50 centimeter, and that didn't really concern myself too much with the accuracy of the data, particularly because I wasn't doing any temporal analysis with that. I was basically just classifying the scene and then bringing out coastlines to understand that process, how accurately you could do that. But obviously, if you are doing temporal change, you would want to have a better quantification of that accuracy. But you're basically just kind of took what the data provider was able to give us. There was no kind of extra georeferencing done to the data set.
Nice to see you again, Andrew. Great
Yeah.
presentation. And great working with you all these years. It was wonderful. Learned a lot. So question for you, and I think we probably talked about this, or you definitely thought about this. I'm curious if you can talk a little bit today about how this method could be used for the retrogressive thaw failures, and if we can automatically detect and watch the breakdown of those over time using this method.
Yeah, there's a few things at play here. Particularly, we're working with pretty high resolution imagery, right? So it's 50 centimeters or so.
Mm-hmm.
That's not something that's like freely available, kind of collected. It has to be tasked basically. Um, so if we think about it from that perspective of an automated way where you download Landsat data or something, for example, this approach may not apply directly to that because the retrogressive thaw slumps are not as well defined. But there
Gotcha.
is certainly characteristics on this data set that kind of pop out of what a retrogressive thaw slump would be. So it's like the coast is really clean and then it kind of gets a little bit messy. And that would be sort of the signature to say, oh, there's a retrogressive thaw slump. And then, go along the coast. And so it can identify it that way. And
Okay.
then there may be like kind of further work to refine that algorithm and maybe train it to say like this is what a retrogressive thaw slump looks like, and then they can pick it out, and then maybe um, come up with a classification scheme that is a little bit more specific to that because there's lots of active areas and inactive areas. Can become pretty challenging and confusing to the computer, frankly.
Yeah, I agree. And it's not as well defined as a beach, water, and a vegetated cliff.
Yeah.
Yeah, okay. I was just curious, and I wanted to hear your thoughts on that. Thanks.
Sure.
Great job again.
Thanks.
Sort of following on from Dustin's, what are the big challenges? You mentioned one, obviously, like tasking, sort of the high resolution imagery. But if you were to want to apply some of these techniques more broadly to other Arctic coasts,
What are the challenges of applying it broadly? Yeah, certainly data access, which you mentioned, but the variability in the coastal environment. For example, the Darnley Bay coast, I came in kind of thinking like, oh, that's going to be the easiest one because of what it looked like, but it ended up being the more challenging one because there wasn't as much vegetation cover. It was more rocky in a lot of cases, so that was giving a bright spectral reflectance, which was very similar to beaches. So finding the water line was pretty easy, but finding kind of an edge otherwise, there would be a lot of blending between the land covers. So I suspect like in the Eastern Arctic where it's more rocky, similar things would happen, but in that case, maybe you don't need a vegetation line. The water line is good enough because it's not really eroding there. Sand spits are also pretty tough to deal with. So yeah, overall, just kind of the variability, and basically the character of the coast. If it's something you can see easily with the human eye, this approach can kind of emulate that. But if you're spending time manually delineating coastlines and you're making like judgments everywhere, that's also hard to emulate. And I expect that would be the case, broadly.
do you know if people have thought about, or you thought about sort of like crowdsourcing any of this?
Definitely try to avoid it as much as I could but that is honestly a major motivation of this is like when you're doing coastal work and you have to delineate coastlines, it's brutal. It's no fun at all. Takes forever. It's kind of inaccurate. So this is a way to outsource it to the computer is sort of my approach. And I applied this to a project that I'm working on PEI, and classified that coast, 3,000 kilometers or so of coast, taking something that's like a month-long process. Basically was able to do it in under 2 weeks by myself. In the past, this has been done by like multiple people over multiple months, and so I'm never going back to doing that if I can avoid it.
So once again, thank you very, very much, Andrew. It was a fantastic presentation, really interesting research. You want to give a round of applause to Andrew. Thank you once again. Yeah, we hope to see you at one of our next webinars.